Hello and welcome to this episode. Central to the idea of neural networks is what is known as a perceptron, and this is what this video is going to be about. I'm excited about this video and the subsequent videos that will follow because at this point I believe we've had enough experience with NumPy, and so we are more prepared for practical hands-on implementation of deep neural networks, and we are going to start that by studying a perceptron. This video is going to be a theoretical explanation of how the perceptron works and how it learns to represent patterns in data. After this video, the next one is going to be about how we implement everything that we learn in this video using NumPy and Python. So I hope you're excited about this as much as I'm also excited about teaching you. Let's get started. All right, so what is a perceptron? A perceptron is basically a single unit of an artificial neuron, okay, that is able to automatically learn weight, that is able to map a given input to a given output. Before we come back here for me to explain how the perceptron works, I want to give you a rehearsal on how we structure our training data set in deep learning. So this is how we structure our training data set. Every training data set has what is known as features, and the features are the columns, and these are basically attributes about whatever problem domain you want to model using deep neural networks. So if this table is a table of students, then basically each column is going to be an attribute of a student. It could be first name, last name, gender, age. Okay, this is all made up. But in this diagram, what you are seeing is each row, which we term as a training example, is using the notation x to a superscript. So if I say S superscript 1, I mean the first training example. And if I say X subscript 1, what I mean is that the first feature, second feature, third. So these are the columns, and then each row is an instance of a training example. Now, a perceptron is able to learn from a particular type of training data, and such training data are what we term as linearly separable data sets. Look at this diagram here. Let's assume that this is a graph representing people who have cancer and those who do not have cancer. The fact that we can draw a straight line to distinguish those with cancer from those who do not have cancer, the fact that we can draw a straight line to separate one class from the other is what makes this data set linearly separable. And this is the first requirement that must be met before the perceptron learning rule will work. It has to be linearly separable. So this graph here doesn't represent a linearly separable data set because it is not a straight line that is dividing them, it is rather a curve. Okay, now the whole idea is we train a perceptron to automatically learn weight, and the weights here are simply the representation of how important each of these features are to the output. So for example, in our cancer example here, we will assume that x1 could be the size of a tumor, x2 could be the texture of the tumor, and x3, I use xn because it could be very large, but then let's assume this is x3. So x3 could be the age of the tumor. And all these things contribute to the tumor being benign or cancerous. And so we assign weight to each one of these input features, and the weight represents how important that particular feature is to determining the resulting class that is assigned to the training example. Let me give you one more example to make it concrete and then we move on. Think of the point where you want to sell a used car. There are two things that you can consider when you are pricing a used car. You can look at the year in which the car was manufactured and then how much mileage the car has done. If the year is not too far in the past, then the price of the car will be higher. If the car has done more mileage, then the price is going to go down. So if we train a neural network or if we train a perceptron to be able to predict if a car should be priced high or low, at the end of the day, you realize that the perceptron is going to learn two weights, one to represent how important the manufacturing year of the car is to determining the price, and then another one will learn how important the mileage that it has done is to determining the class that has to be assigned to the pricing of the car. So I hope with these examples, diagrams, you have gotten the picture of what I want you to know so far. Okay, so now let's go ahead and then see how the perceptron learns. The perceptron learns by, first of all, assigning random numbers to the weight. They are usually zeros or very small random numbers. So you start off with random numbers or zeros, and what we first of all do in a perceptron is to perform a linear transformation or a dot product of the input data with the weight. So what happens is we multiply x1 by w1 plus x2 by w2 plus x3 by w3. Okay, this is what we do. That is the linear combination. And so this formula here is what has been written simply here. And the next thing we do is to add another term, b, which is known as bias. So b is the bias. And the bias basically introduces flexibility. Okay, so it introduces flexibility, and I'm going to explain that. Let's say I give you two numbers, x and y. And I tell you that multiply two numbers such that their output is never 0. You know that this condition can never be met if any of these is 0. If x is 0, then it is 0. If y is 0, then the product is 0. But for you to be able to multiply any two numbers and never produce a non-zero output, we need to add a third term, which we call the bias, so that it is never 0. So if this is 0, yes, 0 times something else is 0, but then plus something else so that it wouldn't be 0. So the only point where the right hand side is going to be 0 is if the bias is also 0. Now we introduce bias in a perceptron to add flexibility to how the perceptron learns the patterns that are hidden in the data. And in most of the deep learning libraries, you realize that you can either turn on the use of biases or you can turn them off. And by default, they are on, and it introduces a lot of flexibility. It helps the neural network to capture a lot of, let's say, difficult patterns in the training data. Okay, so now we do this linear transformation plus the bias, and then we store it in the variable z. So this is what happens at this stage. And then the next thing that happens is that it goes into a threshold function. A threshold function or a decision function. And what the threshold function does is, that is where the decision of the final class that is assigned to the training example is made. So the way the threshold function works is very simple. It returns 1, it assigns 1 if z is greater than 0. Otherwise, it assigns a 0 to it. So this is how the threshold function works. First of all, the perceptron is going to perform this linear combination of the input and the weight plus the bias, and that is what is known as Z. And the linear function, or the threshold function, or the decision function, is going to check if Z is greater than 0. Then it says, yeah, because Z is greater than 0, you are in class 1. Otherwise, you are in class 0. So this is where the decision of which class to assign to the training example is made. Okay, great. So at this point, the perceptron comes up with a predicted output Y. Mind you, we have our original training data labels. That is what you saw in the diagram that was here. In the table, we had input features, and then we had output, which were 0 and then 1, representing the two classes that we want to be able to distinguish. So the perceptron is going to do the linear combination, come through the threshold function, and then it's going to make a prediction of a class or a label that it is assigning to the input data. Okay, that is great. Now the question is, how does the perceptron actually learn? Because I mentioned that we start off, I mentioned that we start off with the weight vector initialized to zeros or random numbers. So how do we make the perceptron learn the hidden patterns in the training data? The way we do that is we do it iteratively. So we start off by initializing our weight to zeros, and then for each training example, x superscript I, we compute the output y hat, which is what I've explained up until this point. And then we have to update the weight and the bias using this formula here. Let me explain to you very well. So the way we do the update is, first of all, we subtract the predicted output from the original output or the label, and then we multiply it by the training example, and we also multiply it by some constant called alpha, and then now we say W, the W vector, which is our weight vector, is equal to W plus, so we keep making this update to our weight vector up until the point where our neural network or our perceptron finishes learning or it converges, and I'm going to explain that. Now this alpha here is also known as the learning rate. The learning rate. So we are iteratively looking for values for the weight vector that is able to almost perfectly represent the hidden patterns in the training data set. And we want to control the rate at which we do the changes, because sometimes you can overshoot and sometimes you can undershoot. So if we don't control the rate at which we make updates to W, you can see that rather than finding the actual values or the closest values that actually captures the patterns in the data, we keep tossing ourselves around, we keep oscillating. So this alpha, also known as the learning rate, controls the rate at which we make changes to W, because it's a number between 0 and 1. So the closer it is to 1, the more frequent updates we do to W, and the closer it is to 0, the less frequent updates we do to W. Now I'm going to use a table to explain to you how the learning actually works. So we start off with random numbers or zeros for the weight vector. Let's look at this table where we have the actual label, let's say is 0, and then the perceptron predicted 0. What's going to happen is, if we put 0 and 0 here, we get 0 minus 0 is 0. So if we multiply that by the training example, we are basically zeroing out everything. And so we don't make any change to the weight vector. What it means is that at this particular point in time, the weight vector is good enough to represent the pattern that matches our training example to its output, because the original label is 0 and the perceptron also came up with 0. So we don't want to touch the weight vector. Let's look at a scenario where the original label is 0 and the perceptron came up with a 1. What it means is that if I put 0 here and I put 1 here, we basically end up with -1. So it is alpha times -1 times x, the training example. And then that is the update that we are going to apply to the weight. What it means is we are basically scaling the weight and nudging it in a direction that will get it closer to predicting the correct value. If the original label is 0 and the perceptron predicted 1, it means the weight vectors, the items or the components of the weight vector are big. Okay, and so we need to reduce it, and the reduction happens because we are multiplying it by -1 and then we are adding it to whatever weight is right now. So essentially it ends up being a subtraction, even though you are seeing an addition here. If the original label is 1 and the perceptron predicted 1, this is similar to 0, 0. So you can see that if I put 1, 1 here, it becomes 0. And so this whole term becomes 0, and we don't touch the weight vector at all, because at that point, the weight vector is believed to be good enough to represent the patterns that are in the data. In a similar way, if it is the true label is 1 and the perceptron predicts 0, then if I put 1 and 0 here, I end up with alpha times 1 times x, which is the training example. So this results in adding something to the weight. It means if the original label is 1 and the perceptron predicted 0, it means the current values of the weight vector is small, and so we need to bump it up a bit. And this is how the perceptron actually learns. So we keep on doing this over and over and over and over up until the point where we say the perceptron learning rule has converged. How do we know that the perceptron learning rule has converged? The way we know is, first of all, the changes that it will be doing to the weight vector will cease, because at that point it would have learned how to categorize every training example into its correct output. Okay, so this is how the perceptron algorithm works. And if all these mathematics put you off and you didn't understand it, trust me, the next video is going to be much better, because we are going to implement this in code, and then you will see these whole formulas being implemented in very simple lines of code in Python, and you will appreciate how the perceptron basically learns. So it is the simplest artificial neuron, and neural networks are actually, to a large extent, a replication of the perceptron so many times, and then they are able to solve complex problems. So thank you very much for watching, and I will see you in the next video.